In this video, we're going to look at the equilibrium's temperature dependence on the decomposition of dinitrogen tetroxide into two nitrogen dioxides. On the right, we'll see this kind of standard stock image. If you have a tube filled with N2O4 and it's colder, it's clear. N2O4 is a clear, colorless gas. As it starts to warm to room temperature, it gets a little yellow, and as it gets warmed up higher, it turns brown. NO2 is a brown gas. And so at colder temperatures, it's clearer because N2O4 dominates. But at higher temperatures, it's brown because NO2 is starting to dominate. Somewhere around the center point, it's a little bit brown, looks yellowish, as we have a mixture of the two gases. Well, using our entropy and enthalpy at standard states, we're going to explore exactly what's going on here. Now, to give away everything at the end, I went ahead and used the NIST workbook, calculated out the free energy and the equilibrium constant accurately if we were to use the real values at those temperatures for entropy and enthalpy, but we're not that far away in temperature. Our standard state's 298, and I just went up and down about 50 degrees. This puts us well into the cold range in order to favor N2O4 and well into the hot range in order to favor NO2. But neither of these is that far from our standard state. So let's do these calculations and find the equilibrium constants at the standard states so we can see why these colors change. For that, I'm going to need some standard states values. The delta H of formation of N2O4, the delta H of formation at standard state of NO2. Well, that is 9.16 kilojoules per mole and 33.2 kilojoules per mole. Neither of these are particularly favorable. They're both endothermic to form from their elemental starting materials. In terms of our entropy, however, for N2O4, that is 304.3 joules per mole Kelvin, and for NO2, that is 239.9 joules per mole Kelvin. At a quick glance, you might think, hey, wait, why is my final product lower in entropy? I'm breaking something apart. I have more moles of gas, but, well, we have two of it. There's twice that amount once we actually do the calculation. The individual NO2 molecule is less entropic itself. It has less atoms to be vibrating and twisting, but having two molecules of it gives far more options for combinations of how fast each one is twisting relative to the other that you couldn't do with an intact molecule. Well, if we want to calculate out our delta G naught, we're going to need to know the delta H of reaction and the delta S of the reaction. So to solve the delta H naught of the reaction, I need to take the products minus the reactants. So there's 2 times 33.2 minus 9.16. So in terms of kilojoules per mole, it is 57.24 kilojoules per mole for delta H of reaction. The change in entropy for this reaction, 2 times 239.9 joules per mole Kelvin minus 304.3, for a difference of 175.5 joules per mole Kelvin. So the reaction does become more entropic because we have more moles of gas, even if each particle of gas is slightly less entropic for just having fewer atoms to be vibrating than our starting molecule. Well, if we want to plug these in, delta G naught at 298 is going to equal 57.24. Let's convert that to joules. So 57,240 joules per mole minus 298 times the delta T of 175.5 joules per mole Kelvin. We'll find that our delta G at 298 is 4,941 joules per mole Kelvin. This is very close to the value calculated with the polynomial from the NIST site. The polynomial is our best fit, so we do expect a tiny change, but that's not terribly significant. Let's similarly calculate these at the other temps. So my delta G, in this case at 248, well, we're just going to use the standard state values so we can compare to how close they are if we had the actual enthalpy and entropy at those temps. 57,240 joules per mole again, this time to 48 Kelvin, 175.5 joules per mole Kelvin. In this case, the free energy at 248, using the standard state values just off temp, comes out at 13,716 joules per mole, and that is just joules per mole for our delta G's. And finally, if we wanted to do it for the 348, again, we're using the same values from our standard state here to approximate, but it is 348 Kelvin times 175.5 joules per mole Kelvin. Our delta G at 348 is negative 3,834 joules per mole. So as we can see, when we compare that to the polynomial derived values, what we find is that it's not too far off, about 5%. So 200 out of 4,000. 5% is kind of the limit of where we like errors to be for various simplifications. So we're at the edge of this, but we're within a reasonable amount. If we didn't deviate from the standard state temperature by too far, then using the standard state values for entropy and enthalpy usually aren't a big deal. Well, let's actually then calculate our equilibrium constants with these. So we'll have a 248, 298, 348. Remember that our delta G is equal to the negative RT ln of K. If we rearrange, our equilibrium constant becomes the negative delta G over RT as the exponent for E. So you divide negative RT over, so we just move the negative up, but it's been divided over with RT. You get rid of the ln by using it as the power to the E. And so our equilibrium constant is equal to E to the power of the negative delta G divided by RT. And so we plug this in for all three of these. E to the negative 13716 joules per mole for 248 divided by, well, R is 8.314 joules per mole Kelvin, and the temp we're using here is 248 Kelvin. So we can solve out that equilibrium constant. We'll find that it is 0.0013. Plug it in for our next temp. E to the negative for 298, it was 4941, so negative 4941 divided by, again, RT. But this time our temp is 298. R is still 8.314. This will equal our K. Our K at 298 is 0.136. And at 348, E, well, our 348 value was negative, so negative will be a positive. This will be positive 3,834 joules per mole over RT. T is 348 Kelvin this time. We'll find that 3.76 is equal to our K. So we can calculate out a few K values here. If we check those real quick against the calculated values, we find that the low temp was 0016 or 0013 with our standard state values used off temp. Not too bad. Standard state temp was 0.14, which basically this rounds to 0.14, so that seems pretty good. And our higher temp was 4, and we had 3.76. So we're off by a little less than 10% there. The air is getting a little bit larger on that side, but we're not too far off. Again, an example where as long as we're close to our standard state temps, we can approximately use the standard state delta H and delta S. What does this tell us about the equilibrium constant, though? Well, at low temp, so let's do constant versus temp. When we were lower at 248, we were down in the 0.0013. But as our temp went up, we climbed 0.14. As our temp continued to go up, we climbed to 3.76. So we'll draw it here off scale. What we find is that our K value is increasing. As our temp goes up, our K value increases. Well, our K is equal to our products over our reactants. So in this case, that K is going to be equal to NO2 squared over N2O4. As our temperature increases, we must make more of our products. And this is nicely centered right around room temp. If we're a little below room temp, then we actually have very little products. We have mostly reactants. And if we have mostly reactants, then we must be clear. As we get to room temp, this ratio gets much closer to 1. The closer you get to about 1, the more equal the amounts of your material. And so we start seeing a lot of products start to show up compared to reactants. Now, we're still dominated by the reactants, but it doesn't take a lot of something colored to start seeing the color. And by the time we're at hot temps, well, we have drastically favored products now. And so now most of the material is going to be the brown colored material, and so it looks brown instead of clear or light yellow. As our temperature increased, we had more energy that we needed to distribute. The original starting material molecule just didn't have as many possible states to distribute that energy in. For a while, that's not terribly significant, but as more and more energy was added, as our temperature increased, we had more and more energy to spread out, and we simply had more options to do so in our products. So despite that it's not favorable to make the products enthalpy-wise, transferring some of the material into products to spread that energy out became very favorable. One way to think about that is that if we have N2O4 and NO2, there's a bunch of energy states for N2O4. And the molecules are occupying some of them. As you add more energy, well, you're going to occupy, you have more energy. You have to spread that energy out. More and more of your things are going to be higher. But there's only so many states readily available. Your NO2, on the other hand, has greater entropy because of the two molecules. It has far more states to spread that out in. So if some of our molecules have broken apart and become NO2, they can spread out and they don't get nearly as high in energy. They remain much more flat, much more distributed. This can be a little odd concept to see numerically or just from intuition of the math. Curiously enough, one way you might see this is if you've ever built a sandcastle. If you ever start to build a sandcastle and you get a little pile of sand, it holds, and you get a little bit more sand that holds, and you get a little bit more sand, and suddenly a bunch of it falls down and levels out. For a while, you can favor being in one position because it's just strong enough to hold itself together. There's a disfavoring in making NO2 because the enthalpy is greater. However, as you get too much of something in one place, the various forces want to distribute it. Gravity wants to pull your sand down and spread it out flat. Entropy wants to spread your energy out. And so eventually we have so much available energy that it is easier to spread it out by making NO2 than it is to keep it in the N2O4, despite that N2O4 is a more stable molecule. This is one of the effects the entropy has on the states of a system. Despite that it is harder to make our product than our starting material, the hotter we get, the more it favors making our product, because it allows the energy to distribute more readily throughout the system. Using our free energy, we're able to calculate out these equilibrium points to figure out how favorable it is to be on one side or the other of this reaction. How close have we gotten to the point where the system needs to start distributing that energy out through more states, versus it cold enough and low energy enough that it's able to maintain its original state?